G'day guys, this will be a fairly simple tension and pulleys example. And here we're asked, what is the tension in the blue rope if the scale reads 500 newtons? So as you can tell, this is our blue rope just here, and this is a pulley which is pinned, right, and this blue rope is wrapped around it, and this pulley is actually free to move, right, it's not pinned to some ground next to it, right, and connected to it is a 200 kilogram mass, and that mass is lying on a scale which reads 500 newtons, okay? So we're asked to find the tension in this blue rope. How do you do it, okay? Well, the way you start any problem like this is always the free body diagram. And I'm going to make a cut selection through here, right, and around here, right, to draw my free body diagram. And I'll be talking in more detail why I made this cut selection like I did, right? But for now, let's just work with it, okay? So let's just draw this cut selection. Well, this is our small pulley, which is free to rotate, so it's not pinned to some ground somewhere, right? And this is our blue rope wrapped around it, like so, okay? And this is the cut selections we made along here and along here. So let me draw that here. That's our cut selection. And out will pop two tension forces equal in magnitude. You've got one force, T here, and another force, T here, okay? And, of course, we need to draw the rest of our free body diagram. We've got this separate rope just here, right? And that's connected to a 200 kilogram mass just here, okay? And that's everything that encompasses our cut selection. So what other forces do we draw on this thing? Yes, we've got our force due to gravity of our 200 kilogram mass, which I'll just draw as mg. M is clearly 200 in this case, right? But we also know, because this 200 kilogram mass is actually resting on the scale to some extent, there will be a normal force acting up back on this mass, and I'll call that N. We'll find out what N is shortly, okay? Now, are there any other forces acting on our free body diagram? Well, you'd be tempted to draw the free body diagram at the pin here, right, and the tension force in this separate rope just here. But notice they're actually internal in this case. They're internal because we haven't made a cut selection along the rope here, right? If you did, then the internal force will be popping out, right? And because this pulley's free to move, it's not connected to the ground somewhere, so there's no external forces acting on this thing, right? And remember, in a free body diagram, you only draw external forces, okay? So these are the only forces acting on our free body diagram, okay? So now we're ready to go into the analysis. We know, because this thing's in static equilibrium, we know that the sum of forces in the y direction must be equal to 0. Well, what are the forces in the y direction? We've got our tension, T here. We've got another one here, I'll do plus T. And we've got our normal force, which is positively upwards as well, right? mg is downwards, so it's negative, so we'll be subtracting that from mg, and that's going to be equal to 0. This becomes a game of mathematics now. We bring the t's together to form 2t, and we bring everything to the other side, and that's going to be equal to mg minus n. And now we're ready to solve for t, and we know that t is just going to be equal to mg minus n divided by 2. Now let's talk about what the value of n is. We know that m is 200, we know g is 9.8, but what's n, right? Well, you can tell from Newton's third law that N, the normal force acting back up on this 200 kilogram mass, must be the same as the force acting on the scale. And to understand why that is, let's draw a free body diagram of just the scale, right? So this is the free body diagram of just, this is the free body diagram of just our scale, right? Just our scale like this. And of course, if you've got a normal force acting back up on the block from the scale, that means there must be a normal force, the same, equal and opposite, right? Newton's laws, acting on the scale itself, right? Now, technically, this isn't a complete free body diagram. Because this thing's connected to the ground, you're also going to have other normal forces acting on the scale itself, right? But don't pay attention to this. The only thing that's important here is the force from the 200 kilogram mass acting on the scale, which is N, which is equal to 500 newtons, okay? I hope I'm not confusing you. I just want to show you that this normal force is 500 newtons, okay? And when you plug this into your calculator, you're going to get T is going to be equal to 731 newtons. Okay, this is our value of the tension in our blue rope. Notice that our orange rope might have a different value, all right? Okay, so that's the value of our tension. I'm going to briefly end this video just talking about other free body diagram selections you could have made, right? It would have been tempting for you to draw a free body diagram like this, perhaps, right? To draw a free body diagram like this, perhaps, because you'd think to yourself, okay, we still include our force due to gravity from this 200 kilogram mass, right? And we've only got one tension force popping out here. Why can't we do that? The only problem with doing something like that is you'd also have to include the reaction forces at this pin, right? This pulley is fixed to the ground somewhere by a pin support. So you'd have a force in the horizontal and you'd have a force in the vertical, and that would be really tough to analyze, right? You'd be really struggling there. By doing a cut selection like this is much smarter because you avoid having to include the reaction forces at this pin support just here. I hope that makes sense, guys. I hope you learned something. Cheers.